So there are many efforts in network virtualization occurring in various standards bodies, a significant amount of research, and as I mentioned. And for instance, there is a working group at the Internet Engineering Task Force in the IETF, which is in fact why I'm not able to be physically in Indiana today. I'm attending this meeting. So a working group called Network Virtualization Overlays, NVO, which is addressing these problems for data centers and for virtual infrastructure data centers. So sort of one of the key examples, use cases in this working group is considering multi-tenant data centers, and in which customers need to have their networks be separated. The sort of standard example is Coke and Pepsi, Coca-Cola Company and Pepsi, using infrastructure in the same data center. Clearly, no one wants their traffic to be mixed together. They need to be strongly virtualized. They need to be isolated. They need to have deterministic performance. And technologies to do that, there are many, but they are still emerging and moving quickly and being standardized. In this space, the ability to reserve bandwidth, to specify bandwidth, and whether it's explicitly specified or with differentiation on a per packet level in terms of quality of service, these are key issues. Again, my observation that the network and the performance of the network is the missing piece is being realized in various ways in various places. So this is an ongoing standardization effort to create technologies that provide this isolation and determinism. Another interesting technology that's emerged recently is what is referred to as software-defined networking. Software-defined networking is essentially making reference to software radios, software-defined radios, in which the frequency band, the encoding of radios, of wireless communications, are defined by software to allow us to partition the spectrum in more flexible ways than is done currently. So that's software-defined radio. Software-defined networking borrows its name from that idea, and it embodies the idea that network infrastructure needs to be programmable and really fully virtualized. So I will say that the dynamic circuit networks, the virtual LANs that Quantum configures, even the technologies in the network virtualization overlays really use existing protocols, existing systems, extend them somewhat to provide this virtualization. And that's a good thing. It's good capability. But software-defined networking really sweeps the table clean from the existing protocols and techniques and says that we really need to have the ability to specify with very fine granularity the way that packets should be handled. So like I said, right now, the frequently used virtual LAN technology it's limited, though. There are only, for instance, 4,000 VLAN tags that exist in the standard. So it's there are 4,096 possible VLAN IDs, and we're seeing today cases where that's insufficient even for a single data center, where there are more than 4,000 entities, networks that need to communicate, and thus this technology, which has served us well, is limited. So software-defined networking suggests that we should be able to create forwarding policies in network hardware based on any field in the header of a packet. So there are 13 fields that are possible to be switched on, and rather than limiting it simply to the VLAN or to the IP network, SDN suggests that we should be able to specify with very fine granularity exactly what sort of forwarding discipline, what qualities of service, what bandwidth should be allocated to any given flow on the network. Typifying SDN and really driving it forward is something called OpenFlow, the OpenFlow protocol. which was developed at Stanford originally, is transforming the networking industry. There have been companies started around this. I guess perhaps in the news, probably folks have heard the developer of OpenFlow originally, whose thesis it was, started a company around this technology, which was acquired, I guess, last week by VMware for $1.2 billion. Here at the IETF meeting, there are many, many discussions about software-defined networking with opinions on both sides, all sides really, about its efficacy, viability, but it's very clear that there's a significant amount of interest. And I'll say it's transforming the networking industry. The networking incumbents who are accustomed to selling a vertically integrated solution, including hardware and software you can't modify, for instance, are seeing this as a challenge to their markets, and many of them are also seeing it as an opportunity to provide capabilities to their clients that they just didn't have before. So rather than, and the idea of SDN really is, rather than sort of playing tricks with tagging and policy and specific rules, you're able to specify, a user is able to specify with a software-based controller exactly what the hardware should do, and at the same time, and maybe more importantly, push those rules into the hardware so that they can be executed at line rate. Obviously, you can build a router out of a Linux box, but it has limited scalability because all of these things have to be handled, all the forwarding has to be handled in software, in memory. So being able to push explicit control into hardware that can handle things at line rate and forward very quickly and efficiently is definitely a disruptive technology, and it's changing various things. And it's certainly the key point here is that in terms of cloud computing, this is really the piece of the puzzle that we were missing. Now we have the ability to virtualize everything and make very specific and decisions about control and performance. So I said quite a few times now, performance, and performance of the network really matters. It's very important. I said before, cloud computing is enabled by high-performance network connectivity. It is indeed. But the ability to use it effectively, the sorts of application environments or services that can effectively be ported to the cloud significantly depends on the network performance end to end. So there are a couple of things to think about in this space. There's the network overhead. How much work does the system need to do to take some bytes of data that are in memory in one process, bundle them up, packetize them, send them across the network, and get them to the destination client or another service layer or another application in a coordinated, another process in a coordinated parallel application. So we have to think about network overhead, and there are many challenges there, and I'll talk about a few of them. The other issue, in a sense, if network overhead can be addressed by, quote, unquote, mere matters of software, the other issue, which is difficult to address with mere matters of software, is network proximity, in particular latency. So the time that it takes to send a byte from one point to another really boils down, after network software overhead and hardware overhead, boils down to the speed of light. And as some folks are fond of saying, we can't bribe God, that's an invariant. So in a data center with a few milliseconds or microseconds of latency between two processes can fail to work at all or perform terribly when distributed over the wide area, and this is simply due to latency. So there are questions there are concerns there that have to be addressed.